Hi, this is an example problem from Chapter 10 about the equations of simple harmonic motion. Pause for a moment and read the question. So we're given an equation here, x of t, which describes the position for any time of an object that is oscillating in simple harmonic motion. And in fact, this is an equation that you can plot. And we can plot x versus t, and you can see here that we've gone ahead and done that. And so if you kind of look and see what this oscillating object is, this little ball at the end of the string is doing as time goes on, it oscillates back and forth, right? We start at t equals 0 at this position. And then it just begins to oscillate, and it goes up and down from then. And you can see that this is a cosine function here. And this thing clearly does trace out a cosine path, as you can see. And so you can understand that equation and the graph are both different ways to view the same thing. All right, so for part A, what we're going to do is we're going to calculate what is the amplitude of the oscillation, what is the ordinary frequency f, and what is the period t of the motion. And we're going to do that by inspection of the equation. Now, so for solving for part A, just to let the graph help us figure out a few things. So here is the location where x equals 0. Over here, this is where x equals a. That's the amplitude. Notice that the amplitude is the furthest distance you get from x equals 0 during your oscillation. So if we go ahead and look at the equation here, and we highlight this term right here, 0.25 meters, well, if we compare that with the general equations of motion here, we can see that the A is the amplitude, and it comes right next to cosine. And that makes sense because cosine, the biggest value you'll ever get there is 1. So the farthest you'll ever get from 0 is when x equals a there, or minus a on the downside. So we can say from inspection, aha, this is our a right here. And we go ahead and write down, so for part A is equal to 0.25 meters. Now we're going to try to figure out what f and t are. But before we do that, we go back to the equation and look. By inspection, whatever the number is that multiplies by t inside the argument for cosine, inside the parentheses, that's your omega. That's the angular frequency. So let's figure out what omega is first. That's multiplied by t. So that's your omega, right? Omega is equal to pi over 8. And that is units of 1 divided by seconds, or inverse seconds if you want. In reality, actually, we typically write that as radians per second, because omega is in radians per second. And now we want to go ahead and figure out what is f. Well, the f is what we call the ordinary frequency. And if we go back to the equations, we can see that there's a relationship between the period and the frequency. Omega is equal to 2 pi f. It's also equal to 2 pi over t. So omega equals 2 pi f. And so solving for f, we find that f is equal to omega over 2 pi. We can plug in the numbers, so we know omega is pi over 8 rads per second multiplied by 1 over 2 pi. And so if we put those numbers into the calculator, well, we can see that the pi's cancel. We get 1 over 16, and that comes out to 0.0625 over seconds. At this point, we drop the radians for ordinary frequency. And we have another unit that we often use. We can also use hertz. So instead of 1 over seconds, you can write hertz, which means 1 over seconds. Same thing. So we got a couple answers here for part A. There's your amplitude, There's your ordinary frequency. And to get the period is the time it takes for one complete oscillation. You can see it over here. If you start t equals 0, you finish at t equals capital T, and notice that you're back to the top again, just like you started out. So that's one full complete oscillation. And T is defined as the reciprocal, or it's related to the ordinary frequency, 1 over f. And so that means 1 divided by 0.0625. I'm going to use the 1 over second units now, because that'll give us seconds. If we calculate that, we're going to end up with 16 seconds. And so that is the period there. So we got part A done. For part B, it asks us, calculate the spring constant. There's a couple different ways to calculate the spring constant. You might use Hooke's law, but we don't know what the force is here. So another way to do that is to relate it to the mass and to the angular frequency. So if we go back and look, not at this here, but at this equation here, if you look at the angular frequency omega, it shows us omega is equal to the square root of k over m, and we can use that. So omega equals square root k over m. Let's square both sides to get rid of the square root, and we're going to find out that omega squared is equal to k over m. And let's solve for k. Multiply by m on both sides, we see that k is equal to m omega squared. Now we know what the mass is here. This is a 0.1 kilogram object. And we know what the angular frequency is. It's pi over 8 rad per second. We're going to square that. And when we do, we'll see what we get. It comes out to 0.0154, and this is newtons per meter are the typical units. Again, we're going to get rid of, whoops, wrong thing. We're going to get rid of the rad here. So let's check and see if those units make sense here. What do we have here? We've got a kilogram per second squared, dropping the rads, right? Is that the same as a newton per meter? Well, let's see. What is a newton? A newton is a kilogram meter per second squared. And then we're going to multiply by 1 over meter. So there's your newton meter there. And if we go ahead and cancel out, we see that indeed we do get kilograms per second squared. So we're good. This is our spring constant here. Now, to calculate in part C, what is the maximum magnitude of the velocity and the acceleration, again, we're going to go back and look at the general form of the equations here. And we can see that the velocity, just like for position, A is the biggest value you ever get because cosine oscillates between -1 and 1. For velocity, it's going to be this part here in front of the sine function. Sine oscillates between -1 and 1. And if we want the magnitude, take the absolute value, it's just going to be a times omega. For acceleration, same logic. What's the coefficient of cosine? It's a omega squared. That is going to be the magnitude of your maximum acceleration. So we can go write those down. For part C, Vmax is omega times A, and Amax is going to be omega squared times A. And we just need to plug those numbers in real quick. And let me pause and I'll go ahead and do that. And putting those into the calculator, we see for the maximum velocity magnitude, or the maximum speed, I should say, it comes out to 0.0983 meters per second. And for the acceleration magnitude, the maximum value comes out to 0.0386 meters per second squared. And again, we drop the rads, and you can see that the units come out as we expect. So these are good. Finally, we're going to look at part D here. What are the position, velocity, and acceleration of the object after 1 second has elapsed? Well, what I want to do is I want to set up specific equations for this problem that take the form shown here. We already know what x is. We're good. We can write down the velocity and acceleration equations now because we know a and omega. Let's go ahead and do that real quick. So for part D, I'm going to go ahead and rewrite the position equation. Let me pause for a second. So there it is for x. Now for v, we know that that's equal to minus omega a sine of omega t. And for ax, that's equal to minus omega squared a cosine of omega t. But we've already figured out the values of omega. Where's it at here? Here's our omega. And we already figured out the value of a. There it is. We can plug all those things in and we'll get the values here. So if we go ahead and do that, in fact, we know what omega a is here. Let's delete that for a second. We'll move this over. So we've got to have a minus a omega. There it is at the top there, part C. It's going to be a minus 0.0983 meters per second. So we've got that coefficient. And then notice that inside the argument, we've got the exact same stuff as we got over here. So we can just copy that. There we go. And for A, we can see that for A, we've got omega squared A over here. And that allows us to go ahead and drag this away for a second. Omega squared A, that is equal to 0.0386 meters per second squared. So that's your coefficient. Then we've got your cosine. And we can go ahead and just copy this again. And so these three here now are the specific equations for this particular problem. Now what I want to do for part D is evaluate each of these equations at the specific time 1 second. So what's x of 1 second? What's vx at t equals 1 second? And what is ax at t equals 1 second? Well, what do we need to do? We need to just go ahead to a calculator and plug in for t 1 second in each case into that equation. Now you need to use radians whenever you do this. And we know that because omega here, this is in rads per second. Okay, so let me go ahead and put these into my calculator. And when I do that for x, I get a value of 0.231 meters. For Vx, I get minus 0.0376 meters per second. And for Ax, I get minus 0.0357 meters per second squared. And so these are our answers here for the part D.